The next thing to consider is the proportions of everything on the planet. You know, the proportions of it all. Now that we know that the atmosphere is very small, of course there are lots of very big things, so let's check it out. Here's our rocky planet, third planet from the sun. Supposing we gather up all of the world's oceans, the world's rivers, the ice caps, the glaciers, all of the water there is in the world, if we could gather it up, how big would it be in comparison to the rocky planet? All the water that the planet has would make a globe about that big. It's not very much, because you've got to remember that in comparison to the planet, the water is spread in such a thin film, that's all the water we have to share. Salt water, fresh water, you name it. How big then is the atmosphere? Well, it's about this big. But bear in mind that this is gas. Doesn't weigh nearly as much. And it turns out that all of the atmosphere is only about 1/600th of the weight or the mass of all the water we have to share. That's an astonishing thought, you know. In fact, if we could squeeze this gas down until it became a liquid so that we could really compare the two, there would be approximately this much air. Liquid. And of course it wouldn't even fill the basin of the Mediterranean Sea. That's how little air there is. But that's what we're stuck with, and that's what we have to work with. Okay. Now, why do I keep going on about the mass of things? Well, it's because you have to understand that to properly appreciate heat energy, you have to know something about the mass of the stuff that it invades. Temperature is only the pressure of heat. It's only like voltage. It's just pressure. But to know something about the quantity or the amount of heat that is circulating around and through our planet, you have to know something about the mass and the proportions of the stuff that it inhabits. Okay? Mass and heat energy. Wait there a minute. I've got a block of stuff. Here's our block of stuff. Can be any stuff at all. It doesn't matter. As long as we know its mass. That's the most crucial thing. I'm going to give this block of stuff a mass of a kilogram. That's a couple of pounds to you Stone Age people. 1,000 grams. And over here I'll draw another little block of stuff and we'll give it a mass of 1 gram. 1 gram. GM for short. So, now, this block of stuff feels fairly benign to me. It's just about room temperature. It has a temperature of 20 degrees Celsius. Let's get this little block of stuff and really cook it up. We'll put the gas burner under it and we'll stoke it up to about 300 degrees. Why not? But don't try and pick it up at home, kids. Much too hot. 300 degrees Celsius. So, which of these two pieces of stuff has the most heat energy in it? Well, this has the highest pressure. to find out how much heat energy is in the stuff, we have to multiply the heat by the mass. So, multiplying 20 degrees by 1,000 grams means that this block has 20,000 units of heat energy. 20,000 units of heat energy. This block has got the power to do work, you know. This little block, pretty hot, probably glowing a dull red, has only 1 gram times 300 units of heat energy. So do you see, temperature alone is not enough to describe the accumulation of heat. Because in a very massive object, a very small rise in temperature means quite a massive amount of heat that's been accumulated in it. And so we come back to our original comparison between the mass of the atmosphere, the mass of the oceans and all the water, and the mass of the rocky planet underneath. And this is a very important thing to stop and consider. So, for example, if the atmosphere should go up on average around the world by 1 or 2 degrees, I mean, that's a serious thing to happen, you know, if it should. But if the oceans of the world, which are 600 times more massive, should rise by just a fraction of a degree, then that's a very, very big deal indeed. And so we are measuring and monitoring and trying to do our best to get a handle on how the temperature of the oceans is faring. It's not an easy thing to do with that degree of accuracy, because don't forget that the oceans, just like the atmosphere, tend to move and to redistribute their burden of heat. That's how heat energy works. Okay, so let's get on to the real mechanics of heat energy.